Assalamu alaikum students, welcome to lecture number 11 of this fluid mechanics 2 course. And in this lecture we have already talking about the compressibility of fluids. We are talking about compressible flows, and in last lecture we saw about different state properties, that how we will find their change whenever we are talking about a controlled volume, and in that controlled volume has a certain amount of control surfaces, for example, or if you are looking at a change of a certain state function, for example, change in entropy, enthalpy, or internal energy, or pressure or temperature, then how will we deal with that change? And we saw that we will deal with them with the help of the ideal state equation, and the enthalpy and internal energy, and the TDS equation that we saw for the change in entropy. Then we derived an equation for isentropic flow, and today we are going to use it in our topic, that is the Mach number. And Mach number, just like other dimensionless numbers, for example, if you look at this equation, Mach number is also a dimensionless number. It is also a dimensionless number, just like Reynolds number. And it is why it is dimensionless, because it is a ratio of two velocities. One is the velocity of an object, and the other is the speed of sound. So it is the ratio of two speeds, so that's why it is dimensionless. And what does Mach number tells us? It basically gives us the idea about the compressibility. It actually helps us to measure the compressibility of a fluid. It helps us to measure the compressibility of any fluid. And normally you would have heard that Mach number is closely related to aircrafts, such as the fighter aircrafts. Whenever we hear a boom, whenever a aircraft is flying in the sky and we hear a boom, then we say that it is in supersonic or hypersonic regime. So what are those regimes and how we define them? They are all defined with the help of Mach number, but how this number is related to the compressibility of fluid is the question that we have to answer first. As you know, we already discussed in the previous lecture that sound that we hear is a pressure pulse. It is a pressure wave that strikes our eardrums, and it vibrates our eardrums, and then we hear a sound. So just like an example, if you take an example of an aircraft, so what does an aircraft do? Whenever it is flying through an air, let's say this is an aircraft, and whenever it is flying through an air, what does it do? It actually disturbs the air around it. It disturbs the air around it, and when it does that, and if its speed is, if let's say the speed of this aircraft is less than or equal to 250 miles per hour, 250 miles per hour, then we consider the air around, this aircraft as it is incompressible, or the density is not changing if the aircraft is flying at less than or equal to 250 miles per hour. But let's say that the aircraft speed exceeds this limit, 250 miles per hour. Then what will happen? The air around the aircraft, for example, this was the aircraft, and the air around the aircraft now starts to compress. The air around the aircraft will start to compress, and as we further increases this speed, for example, let's say if we take it equal to the speed of sound or above that, then a shock wave in this compressed air is generated, because the speed is so high that the fluid compresses so rapidly that a shock wave is generated, and we hear a boom, a small blast, whenever an aircraft crosses this regime, or its speeds become equal to the speed of sound, because of that high compression, or that high change in density results in the generation of a shock wave. So that's why this number is related to the compressibility of fluid, that with the help of this number we can say that how much of fluid that is flowing around an object, or an object that is flowing in a fluid, that is moving in a fluid with the speed of sound. Then it will actually compress the fluid around it, and it will generate a wave as such that it will be a shock wave, and then we will hear the sound of that shock wave. So again, the Mach number is related to the compressibility effect in a fluid. It helps us to measure the compressibility effects in a fluid, and it is a ratio of two speeds. One is the speed of an object and the other is a speed of sound. So in this lecture, what we are going to do, we are going to first derive an equation for a speed of sound by the help of our Reynolds transport theorem. We will actually consider a small weak pressure pulse, and we will see the effect of this pressure pulse when it is moving in a stationary fluid, or it is moving relative to a moving fluid. So we will apply our mass conservation equation, momentum conservation equation, and we will derive an equation for the speed of sound, and then we will derive some other terms that will be useful for us in the coming lecture. So what we will do, we will apply this Reynolds transport theorem to a certain scenario, and that scenario will be that we will consider a small pressure pulse, a one-dimensional pressure pulse, and that pressure pulse is moving in a certain direction, let's say, and the air that is already disturbed by this pressure pulse is P plus del P, and the density is P plus rho plus del rho, and with the speed of sound, let's say that this pressure pulse is moving, and the pressure ahead of this pressure pulse or pressure wave is P, and the density is rho, and the velocity is 0. So this is actually, as we said, if we define a control volume for this pressure pulse, if let's say this is the control volume with an area A on both sides, and this is the area. This is the area that is disturbed by this pressure pulse right here, a pressure wave, and this is the air that is not for the time being disturbed. As this pressure wave will move through this region of air, then its pressure will be changed and density will be changed by the values that is shown here. So we will first consider a weak pressure wave or pressure pulse, and we will see that what happens to the fluid that through which this pressure pulse flows, and then what happens to a fluid that is moving relative to the pressure pulse. So then we will apply the control system and the control volume analysis. This is the continuity equation. There we will apply this equation, and as we said, the changes in fluid properties across a sound wave are very small compared to the local values. These are actually very small changes, and by this statement we mean that the sound that we hear in our daily use, for example, we talk to each other, so these are very small or weak pressure waves that our ears can bear. So these are the two cases that we talked about, and in the first case right here, this is the first case. This is the weak pressure pulse that is moving into the air is stationary, and this is the region where the air is not disturbed by this pressure pulse. Then we say that this region of air is already disturbed by the pressure pulse, so that's why its pressure has changed by an amount del P, its density has changed by amount del rho, and its velocity has already changed. So this was the first scenario in which the air is stationary around this weak pressure pulse. Then in the second case, this is the second case, this pressure pulse is moving with a certain velocity, and the air around this pressure pulse is also moving. So if say the air is moving in this direction and the pressure pulse is moving in this direction, then this will be the disturbance that the pressure pulse will create in this moving fluid or this moving flow that is being disturbed by this weak pressure pulse, and that is disturbs this moving flow by amount del P by amount del rho, and the velocity will be C minus del V. That is the speed of the air, and this del V is the speed of this pressure wave. So this velocity will be the difference of these two velocities. And then the air that is being undisturbed for the time being, its pressure is P, density is rho, and velocity is C. So these were the two cases. In the first case, that is being named A. In case A, the pressure pulse, the weak pressure pulse, is moving in a stationary fluid, and it has disturbed a certain region of the flow, and a certain region of the flow will be disturbed when this pressure pulse flows through it. Then in the second case, the pressure pulse is flowing in this direction in a flow that is moving relative to it in this direction, and it has again disturbed this flow by amount P plus del P, rho plus del rho, and C minus del V, while the undisturbed region is again having values of pressure P, density rho, and sound velocity, that is a velocity that is equal to the speed of sound. So these are the two scenarios, and now we are going to apply the control volume analysis on this second scenario. On the second scenario, what we are going to do, we are going to do these two control surfaces having area A, and we are going to apply the first the conservation of mass equation and derive a certain value. Then we will apply the conservation of momentum equation on this scenario and derive a certain quantity that will help us derive the value for the speed of sound, or an equation for the speed of sound. So let's do that. So here again we are going to take this case right here and apply our Reynolds transport theorem of mass conservation. So this is our Reynolds transport theorem for the mass conservation that you are already familiar with, and we are going to apply this conservation of mass on these two control surfaces. This is our control surface 1, this is our control surface 2, where the flow is going in and out at this region 1 and 2. So for the mass conservation, we are going to say that the overall mass is conserved of the system, because we are talking about the law of conservation of mass. So the total mass is conserved of the system, so this term will be equal to 0. The flow is steady. We are going to consider a steady flow, so this term will be equal to 0, and we are going to apply the control surface term on both these section 1 and section 2 and write an equation for this term. And here for control surface 1, the density is rho, the speed of sound is C. So we are going to replace them with these values, and the area is A as already mentioned. Then for control surface 2, the density is rho plus del rho, and the velocity is C minus del V, and the area is A. So we are going to write an equation for that. So this is at the inlet, this is at the inlet, this is the density, area, and velocity. As you already see, density, area, and velocity in this term, and here the change in density at section 2, area, and the change in velocity at section 2 right here, as we already mentioned. We are going to rearrange these terms, multiply these terms, and then rearrange this equation like this, and after simplifying certain terms, then we can actually write this equation like this. This is from the conservation of mass. Then what we are going to do, we are going to apply the conservation of momentum on the same scenario, on this scenario, and this is the Reynolds transport theorem for conservation of momentum, and now this left hand side will be equal to the summation of forces. This is again steady state flow, and this will be equal to m dot, that is the mass flow rate into velocity. So we will arrange, we will apply this change in system with respect to time, and the change that happens across these two control surfaces, that is control surface 1 and control surface 2, and write an equation for these scenarios. So here on this right hand side, this is delta F, the summation of all the forces. So here the forces will be written in terms of pressure. So this is pressure, this is area. So the force applied on this section 1 is PA, that is the pressure force, and on section 2 that is P plus del P into A. So this is how we are going to write the summation of forces. And then for the control surface integral, we are going to write terms in terms of m dot v. So this is as we say, this is for section 1, that is the density, velocity and area, density, velocity and area multiplied by the velocity. So this is at the inlet, so that's why it's negative. That's why it's negative. So the flow flowing in is negative, flow flowing out is positive, and the flow flowing out for the of this control surfaces is this is the density, as in this term, the velocity c minus del v, c minus del v, these two are the velocity terms, multiplied by the area of the control surface 2. So this is how we write this equation in terms of conservation of momentum. So simplifying this term, we are going to get this term right here, and then the continuity, the equation that we got from continuity, and the equation that we got from the conservation of linear momentum right here. We are going to compare them, and from them we get the term for the speed of sound right here, and that is equal to c square is equal to the small change in pressure due to the small change in density. So as you can see, the change in density is related to the change in pressure. So whenever the pressure changes around a certain aircraft, because when an aircraft moves through a fluid, the fluids will be the air particles or whatever the fluid is, the particles will the particles surrounding that flow aircraft will compress, their pressure will change, and that will ultimately result in the change in density. So this is what this equation physically means, that the change in pressure around the aircraft will result in the change in density, and that is what the definition of the speed of sound is, and that is the term that we are going to use for the speed of sound, and equation that is going to be used for the calculation of the speed of sound. So that equation was derived with the help of linear momentum equation that we derived with the help of Reynolds transport theorem, and the continuity equation that we also derived with the help of Reynolds transport theorem, and applying this to the scenario where the pressure pulse is moving with respect to the flow of the air or whatever the fluid is. Now in the one scenario can be that the flow is compressed isentropically. Isentropically means that the entropy is constant. So the equation that we derived will have a subscript s that represents the isentropic flow. So now let's write an equation that we derived for the isentropic flow, and that equation was that P over rho k is equal to constant. That equation also had pressure terms and the temperature terms, and they were all equal to a constant. So this was what was derived when we compared two S2 minus 1 equations. As you remember, one was for the constant pressure and one was for the constant volume. When we compared these two equations, we got these values, and we compared them because we saw that the change in entropy was neglected. So when the change in entropy was neglected, the flow was isentropic. Then we compared these two equations, and we had a term in which the density, pressure and temperature were all related to a constant, and that was a very useful term in which we can find the change in density with respect to change in temperature, and the change in pressure with respect to change in temperature and density. So that was only because we considered an isentropic flow situation. So now again, considering that isentropic flow situation and using this equation, we can actually derive another term for this speed of sound, and in that scenario we can also include the pressure and temperature effects in the speed of sound. So let's say that this was our term inside the bracket. If we apply the partial differential on this equation, let's say that if we multiply and divide this equation with partial or partial rho, so this will be partial p constant into partial rho power k over partial rho. We multiply and divided this equation we multiplied both sides of this equation by partial over partial rho. So what will happen? We will be left with this term on the left hand side, and we can actually simplify this further, and this can be simplified as constant. By applying the derivative on this, we will get k into rho k minus 1, and as you already know, this constant can be replaced, as we saw that p over rho k was equal to a constant. That was the term that we derived when we considered the flow as isentropic. So by writing this term instead of the constant right here, we can actually get that p over the density over the specific heat ratio, that is k power k minus 1. So this can be further simplified, and we can write this that let's say that p over rho power k into k, and we can actually write this in terms of multiplication, that rho power k and rho power minus 1. We can actually write this rho power k minus 1 like this too, by having a multiply sign. So this rho power k and rho power k cancels. This rho power minus 1 can be written as p over rho multiplied by k. So here, as you can see, that this p over rho represents what? P is equal to rho RT. We know that from the ideal state equation, and p over rho will be equal to RT. So by substituting these terms with RT, so what we get? We get RT k. So here the partial p over partial rho comes out to be RTK, and now replacing this partial p over partial rho in this equation right here, so it comes out that C is equal to under root RTK. So this actually gives us the with the help of this equation, we can actually find the speed of sound in different mediums. For example, now in this equation we have the universal gas constant, so that value is specific for every gas. So we can use that value at different temperatures and different specific heat ratios for certain gas to see the effect of temperature and the value of the effect of the universal gas constant on the speed of sound. And if we, and this is the equation that we already derived, that the speed of sound is equal to under root the universal gas constant, temperature, and the specific heat ratio. And if we look at these two graphs here, the the universal gas constant is given, and the universal gas constant is greater for hydrogen and it is greater for helium, and then here has the smaller value of R when it comes to helium and hydrogen. So what does it tell us? It tells us that the speed of sound in hydrogen will be greater than the speed of sound in helium, and the speed of sound in helium will be equal to greater than the speed of sound in air, because of the higher values of R that these two gases have. And then if we look at these two graphs here, the value of k is greater, but it is not that much, and the value of k for air and hydrogen is the same. So the main contributing factor is the universal gas constant in this equation, and the gas that is having higher value of R will have the higher speed of sound in that gas. So this is why this equation gives us another dimension by looking at the speed of sound, that now we can actually see the effect of the speed of sound with respect to the universal gas constant, the temperature that a certain gas have, and the specific heat ratio. We can also look at it by using another term, and that is the bulk modulus. And bulk modulus actually deals with the compressibility of the fluids by, let's say, changing the pressure, then what happens to the volume of a certain fluid. But here we will not be talking about the volume, we will be talking about the density, that by changing the pressure, what happens to the change in density. So let's look at this, that is the definition for the bulk modulus, that a change in pressure results in the change in density from rho to d rho. So this can be further written in this form, and we can again write this speed of sound equation in terms of the bulk modulus of compressibility, because it also deals with the compressibility of fluid, that how much pressure is applied, and by that application, by the change in pressure, how much the fluid is compressed. So we can also see that the compressibility, the bulk model of compressibility with respect to the density can also be equal to the speed of sound. And what does this equation tells us? This equation tells us that the fluids or anything that is not too easy to compress, the speed of sound will be greater in that scenario. For example, let's say that the speed of sound is larger in fluids that are more difficult to compress. So for example, if we take air and if we take water, so water is difficult to compress, very difficult to compress as compared to air. So the speed of sound in water will be more because of its high bulk modulus. Because why it has a high bulk modulus? Because it will require very high amount of pressure to change the density of water. So it will have a high value of the bulk modulus. That's why the speed of sound in water will be higher as compared to the air. You don't require that much pressure to change the density of air, so the value of the bulk modulus will be low in that case. So the speed of sound will also be low for the air as compared to water. So these are the equations that are related to the speed of sound. They give you the same thing, the speed of sound, but they can be used in different scenarios. For example, these equations can be used for different gases having different temperatures and specific heat ratios, and this equation can be used for different type of fluids that is having different value of compressibility. So this was related to the speed of sound that we had in our Mach number, that is the velocity of the object, and the speed of sound. So this was related to the Mach number, and the Mach number, as we already said, tells us about the compressibility of the certain fluid. Why? Because the sound is a pressure pulse or a pressure wave, and as much as the fluid around a certain object is compressed, it means that it has a high velocity, and that when that velocity exceeds the speed of sound, it sends a shock waves in the compressed air. That the pressure pulse generates a shock wave, and we hear a sound, a boom like sound, that we say that now the Mach number of a certain aircraft of a certain entity has exceeded 1, the value of 1. As far as the Mach number remains 1, then that is in the safe regime for our air. And then after this lecture, we are going to discuss different regimes based on the Mach number, and how the compressibility of the fluid is related to this Mach number, this dimensionless Mach number.